Damas y caballeros, ladies and gentlemen, it is a pleasure for me in this beautiful country, Colombia. Even in our country, Colombia is a very familiar country because of its very delicious coffee. I drink not only Japanese green tea but also coffee every morning, especially my wife, of course, made in Colombia. Colombia is very popular not only because of coffee, especially emerald. Japan is a small island nation. Land area is only one third of Colombia, but many metal deposits are there. Japan was a leading mining country. This story was 100 years ago. But now we have more than 5,000 abandoned mines. Polluted mine wastewater outflow is found at 450 of the sites. Many cases, no more mine owners are missing. Responsibility often isn't clear. For today's topic, Firefly Village, Misato District, Joko Shinagawa City, Shikoku Island. Misato District is green with a beautiful water environment and fireflies. I'd like to talk about a little bit about Japanese typical firefly Genji Botaru. Their children live in clean, flowing water. Their bait is freshwater snails. Parents eat nothing but only drink water. In Japan, firefly is a typical biological index of water environment. This is our water flow direction in Misato District. Here, in the beginning of every summer, we can see thousands of fireflies there. But strangely enough, no fireflies found along the main river. This mainly water flow rate is moderate. Water quality looks good. Good enough for snails and fireflies to survive. But in order to answer this question, local government made a chemical analysis of river water. Water of the main river does not contain harmful chemicals. Then, local university team with biological research, they found some trees emit special chemicals to harm insects, but they couldn't answer why exclusively firefly do not exist along this river. In our research procedure to answer this question, they are doing all steps of research. Firstly, field investigation for geological and geographical characteristics and water and sediment samples. Then after chemical analysis of water and sediments. Third, based on those analytical data, they performed model calculations. Then they tried to propose a countermeasure. Their observation area, Misato District, it is very typical small Japanese mountain village. It is 1,000 people. Geology is crystalline schist. And they say geographical fieldworks, they found small abandoned mines along the river. And its mining period was 100 years ago. Commodity was copper. There are plenty of
Copper
carbon
pipe.
pyrite. And from based of this observation, they found acidic water continuously growing and flowing. This is a flow of mine wastewater. Flow rate is 25 liter per minute. pH is around 4. We performed an investigation 4 times, and each time they took water and sedimentary samples from 25 points. Today we will focus on this area. Point A means mine water, and H1 is non-polluted water, river water. H2 is 100 meters downstream of the confluence of mine water and natural river water. H3 is far downstream, 3 kilometers downstream. This is the confluence. Mine water come like this to the main river flowing like this. So point A is this direction and point H1 is going this direction. Those are the result of river water. This is Japanese drinking water standards. H1 natural river water. There are no heavy metals there.
Very few.
We analyzed many heavy metals, but we found only 4 heavy metals concentrated in that mining water. And in mine water, copper is higher in concentration, so we can't recommend you to drink this water. Downstream, at point H3, again, the water quality again is good enough. Maybe water itself is not much problem, not only for people, but for fireflies. How about a result of dissolved magnetic components? The vertical axis is concentration standardized value, not in ppm, but standardized to show various major components in one graph. In mine water, especially on magnesium, calcium, and silicon, it is very high in concentration in mine water. That's downstream of confidence. It is already diluted and almost slightly about the ground level in this area. NH2 water seems simple dilution of mine water, and it is and together with natural river water. But what about the result of heavy metals? Again, mine water has very high concentrate of copper, manganese, and zinc.
Copper.
In point H2, a little bit downstream of confidence, it is almost the same level as the river water. No heavy metal supply from mine water. Where have heavy metals gone? Removed?
Stoichiometric.
To answer this question, this leads us to stoichiometric calculation to calculate the
Quantify
duration
the
removal dilution effect. This is the calculations. After ideal conservative mixture, this concentration is expressed by this equation. C is concentration, F for flow rate, and what is US? US is upstream, in this case, with H1, point H1, and the T is tributary of mine water, and DS is downstream, point H2. So we can calculate using H1 concentration and A concentration and flow rate. You can calculate the downstreaming in our mixture that is ideal and conservative. In the control by conservative mixture and simple dilution, of course, concentration is measured to calculated concentration. This ratio would be 1. If removal by precipitation or absorption happened, measured concentrations will be calculated with a different reference. And if additional happens, major concentrations would be larger or higher than the calculated concentration. Of course, there is an important condition, measured viability. Water sampling,
accurate
after
chemical
analysis, accurate measurement of water. They calculated some mistakes in it, that this calculation result also evaluates our field measurement and analytical technique. How about the results? This one is a conservative mixing. In major components, it is fitting and conservative line. We can say that those are controlled by simple dilution of mining water together with the natural river water. But how about flow? All field measurement and analytical technique are satisfactory for this sake. And for heavy metals, how about the result? Yes, they far below the conservative line. That means renewable reaction happens something. Maybe precipitation, but we had to confirm if dissolved heavy metals precipitate at the confluence. Heavy metal concentrations in rivers, sediments at H2 must increase. But how about analysis of river sediments? Again, this is the same diagram for river sediments. At the mine water area, the river sediments concentration is a little bit higher than land river. That as a confidence area, copper, zinc are very high concentrated. Precipitation of confluence happens there. We must see precipitation reaction of heavy metal is proceeding at the confluence. Then next, what make heavy metals precipitate at that confluence point? We'll see it by thermodynamics. There's a simple thermodynamics. This is a pH diagram for iron. Horizontal line is pH. Vertical line is reduction. And this white area is iron dissolution. Gray area is precipitation. Insoluble. How about the mine water? In dissolved area, in this area, dissolved iron will be dissolved in water. But for natural water and confluence water is very good area, so iron is not dissolved there. It goes down by precipitation. Increase of pH caused insolubilization of iron. How about the heavy metals analysis? The index, saturation index is always 0 if they precipitate. Manganese, zinc, and copper slightly over 0. We can say pH increases, heavy metals are insolubilized. Neutralization causes precipitation of heavy metals. For high concentration of heavy metals, there is copper in river sediments. Freshwater snails and firefly cannot survive. They are very sensitive to copper. Key is not water, but sediment. But for based on these results, what can we do? Specific problems in this site, the characteristics of mine water, high concentration of those 4 heavy metals, and also strongly acidic bisulfuric acid. And most important is lack of money. No mine owner, no payer. The point of countermeasure is inexpensive. Low environmental impact. The methodology should be promote heavy metal precipitation before flowing now to the river. The image of neutralization facility. Very gorgeous neutralization facility, as in Japan we have many, but in this case it was impossible for lack of money. To promote heavy metal precipitation, it dig a small hole in the mine water flow. The input neutralizer made with limestone
100 ton per year.
100 concrete year and 400 tons per year.
To see the environmental impact efficiency. The sample is the reaction and the efficiency is natural water as grease area. This is the result. The facility expected facility area, the mine water pH is about around 0.47. But after the treatment, it came to 6.88. In this case, the copper removal efficiency is around 80%, and therefore the heavy metal was around 100%. And the precipitation, it was around 0.23 a ton per year of oxide or sulfate. The environmental impact is 32 ton per year of dissolution. So this 32 point dissolution, 30 ton per year dissolution, would be an impact not so big. That means that around the main now presently, the main river carries in concentration is 18 ppm. But after this treatment, it will go up to 20 ppm. 20 ppm of calcium is a typical for a Japanese river water. So environmental impact is not so much. Maybe it will work. Conclusion. Dissolved heavy metals in mine water precipitate at the confluence by natural neutralization. Most dissolved heavy metals are removed at the confluence area. So So for a countermeasure, the method is neutralization and precipitation is a more efficient way. And the removal efficiency of iron, of copper is 80%. For other elements is around 100%. Thank you for your attention.